Hello, welcome to this new subject, plant processes and renewable energy. We short this subject as PPRE. I am Dr. Wang Yanmei, and I'm going to go through this subject only for topic 1, which covers chemical analysis. This subject, topic 1, covers 3 main parts. First one is introduction, followed by several general parameters we are going to introduce to you used for biodiesel production. And the last one is analysis techniques involved for these parameters. Okay, now we are going to move on to the first section, which is introduction. I think I will hide this toolbar for us to see more context on the page. First, we are going to introduce you the concept of the biodiesel. Biodiesel is a newer considered compared to the conventional fossil fuels. This biodiesel actually is direct compared to the diesel itself. We know as the fossil fuels, basically the mine for somewhere, then somebody will dig it into oil miners, then go to refinery, got the diesel for people to use as energy resources. Biodiesel, literally from the word itself, is from the bioprocess produce the diesel. Okay, this is a renewed conventional fossil replacement. Actually, this is a very important concept because it contributes to our sustainable planet, which can reduce the human carbon emission concept and surely will help to achieve the carbon neutral, or sometimes we call it carbon zero balance target, which now is a very hot topic in our energy field. How to produce this biodiesel is one of the topics we are going to introduce. Basically, say the biodiesel is produced from the fatty acid ester. Okay, this fatty acid ester is from some feedstock. Feedstock here means the starting material or the raw materials here. Okay, and what we want is the biodiesel produced or generated. They should have the similar physical and chemical properties. So basically, they should be equivalent quality compared to the petrol-based diesel now on the market sold. So what type of the feedstocks we can use? Now the conventional one is the diesel itself. We are going to use the bio or biological resources, which can be edible oil or non-edible oil, or some of the animal fat, such as the fish fat, or some of the other living stocks fat, or some microalgae. Here we want to emphasize one concept is the waste cooking oil. And we are going to continue to introduce this concept in the following slide. The edible oil, or when our family members go to the supermarket somewhere to buy the cooked oils, whether it's vegetable or some other sources, we are going to use it for cooking. But you imagine the food court or the canteen use some of the oil to deep fry some of the chicken wings or some other or some other things. Leftover oil is considered waste cooking oil. And from this process, we know this oil underwent a very high temperature processes. And very commonly, they were mixed with some of the kitchen waste or some of the salts inside, such as sodium chloride, is very common compounds found inside. if anybody want to dispose this WCO, waste cooking oil, directly into our environment, it surely will create a lot of environmental issues, which is surely the contamination or the pollution concerns. On the other hand, if we are going to take this waste cooking oil as our biodiesel producing or production resources, starting materials, it can be a very good feedstock because the price almost as free, basically the low cost, low price to purchase it is a very economical process. You will take it as the starting material. For the fresh cooking oil, the main components or main compounds actually is the ester. Okay, it's called fatty ester. The common ones is the glyceride. I will use the pointer so we can see clearer here. So this glyceride is something look like this. This one called triglyceride. Tri means three, right? Because 1, 2, 3. There are 3 positions can be form this ester bond, which you just learned from your organic chemistry subject. Okay, and this bond is, we know it's ester. We did not emphasize this reaction, but now we introduce you during cooking. This moisture, which means water, okay, this water can hydrolyze this bond. Basically, they will break this ester bond, so they will produce some of the free fatty acid, we call the FFA. And this FFA, free fatty acids, the general formula will be look like this. They are undesired. Basically, they are not very friendly or welcome to appear in our biodiesel production. One more reason is this free fatty acid will form some soap or salt format. The problem when we carry out this biodiesel production. I think later time you go to our TP campus, the pilot plant site, you will understand it in more detail in a better specific way. This general reaction formula here can give you a rough idea how this reaction goes. Basically, it's triglyceride, which is the ester here. They will react with the water. Basically, water will hydrolyze, basically break this bond. So this glycerol will be form itself as the alcohol ferment. And this 1, 2, 3 parts will be 3 of the fatty acid. Okay, now we know the waste cooking oil have some of the issues. The free fatty acid be there is causing the soaping problem. The water content, if it's too high, they will surely hydrolyze the ester and you form the free fatty acid. And Z means the free fatty acid and water content, okay? They will make the following steps, which called esterification reaction, be very difficult. So analyze them and pre-treatment of this waste cooking oil will be needed. Actually, they will be a must if we want to carry out this production. Just now we introduced the concept of the trans-esterification. We know esterification, this word from the organic chemistry, basically forming the ester from the acid and alcohol. Trans-esterification means we are going to exchange one part of this ester. So means what? This triglyceride look like this, right? This is the alcohol moiety. The other side is the acid. The R1, R2, R3 is the long CH aliphatic chains. So we are going to change this alcohol part to a simpler ones. If we reading the words by words of this 4 bullet point, the second one is triglyceride with the alcohol and form a diglyceride. Basically, they clip off one bond off. And the di products, they can further clip one more to produce a monoglyceride. The monoglyceride can be further chopped down to be another molecule of the fatty acid esters. Fatty acid, these 3 parts. If they clip off, that means hydrolysis. But if we are going to trans-esterification, basically they are going to replace this part with another part of the alcohol. Okay, so it means this alcohol will interact with whatever they freed up this end, they will form another fatty acid esters. I talked a lot, and reading these slides here is a bit wordy, right? So we try to make it easier to see whether you prefer which way. We use the graph here, try to illustrate a little bit more. So basically say triglyceride here can react with alcohol under the condition of the catalyst, which normally use alkaline or acid, just use one of them, okay? So this reaction will give us the fatty acid ester as the biodiesel as a product. And one more product here is diglyceride. And this diglyceride can react with another molecule of the alcohol. Further, with this catalyst, they also form this biodiesel fatty acid ester here and reduce one more grid, which from tri to di to mono. So the monoglyceride will be here. And this one is surely is not our final product yet. They can further react with the alcohol and also produce the third step, basically the third molecule of the fatty acid ester plus the final of the alcohol here, which is glycerol. I hope now you have a basic idea what is called trans-esterification here. If we are going to use this formula or use this reaction, structure reaction scheme to elaborate this reaction, the triglyceride, the structure look like this. The green box basically is highlight the fatty acid moiety. When we say moiety means part. Ester have 2 parts. One is alcohol part, one is the acid part, right? So this acid part, they will react with these alcohols. So the alcohol here, normally when we say the alcohol, we want to use the simpler alcohol instead of this glycerol. Okay, so the common ones use the methanol or ethanol. But for our case, particularly in TP case, we use the ethanol. Okay, I believe the reason you possibly can imagine already, the safety issue. The ethanol surely is sounds and practically is safer than methanol. That's why in the teaching purpose or in our practical purpose, we use our ethanol. So this ethanol will replace the glycerol position, so can be replaced from here. The final of this fatty acid ester, okay, fatty acid ester means fatty means this part, ester means this function group. Still remember, this is part from the alcohol. If we are going to further look at this alcohol part, actually this CH2H5 and C2H5O will become this orange blocked, this moiety. Basically, this structure, this part come from this alcohol. And C double bond O plus this longer chain, they are coming from the fatty acid, the fat part. The whole molecule here is called biodiesel or fatty acid ester. They are common name called biodiesel. We treat these fatty acid esters as biodiesel. So now we roughly have the idea about what is biodiesel, what is waste cooking oil, what's the problem or issues we worry about with cooking oil, and we roughly have the idea about this trans esterification. So now we are going to move on to the next section, which is the general parameters. We are going to understand or get to know some of the parameters regarding or related to the biodiesel production. Okay, this part is really a list of the few general parameters, literally, okay, because there is a more comprehensive or more complex parameter list on the standard. Now it's adopted in an international way, but due to our time limitation or our subjects considering, we cannot talk about full spectrum, basically all of them. We only choose several or only a few. Now here we list 4 bullet points rather than the whole list of the checklist parts. The first one, we surely want to know the fatty acid, okay, especially the free fatty acid, which is hydrolyzed products from the water content, basically it's moisture in the waste cooking oil. This part we are going to understand them, or at least to know some of the water contents, for example. The reactants in the trans-esterification reaction, the ethanol part is a very important reactant, and I hope you will learn how to analyze this in our following section. The last point, the products of this trans-esterification reaction is two. Still remember, one is glycerol, which here we call side product or byproduct. They are the same meaning. Basically, it's something they generated, but it's not what we really targeted to. The other one is the main product, which is the pleasant or what we want. We call the main products. That's called biodiesel. We also know that it is the fatty acid esters. And these products in the trans-esterification reaction, this glycerol and biodiesel, we are not going to discuss it in this topic because they are more standard, not because they are not important, okay? They are important, but we have to choose, we have to be selective. That's why we just, this part, and we are not going to detect those parameters now, currently. Okay, now we should move to the analysis techniques. So basically, what kind of technique we can use or what method we can use to detect these parameters. Just now we highlighted. Look at these 3 parameters first. Okay, we really simplified it a lot. We need to know them one by one. Some are very extensive way, some just understanding way, some is on the reasonable way, I would say. You will tell from our lecture notes how much we emphasize on it. You will know which part we need to emphasize more. Okay. For the waste cooking oil or the feedstock, for example, we do have a lot of the standards which is well recognized in the international or worldwide. One is, for example, this one called the EN, which called European Union. Is very well recognized in the European the area. They have their standard method. Another one is ASTM, which stands for American Society for Testing and Materials. It's also a very well recognized society or standards in the American side or the areas. Both of the areas are quite well known for the industrial. So here we are going to introduce some of the references. We are not going to test you to must remember this standard or the other standard, but this is somewhere we adopt why we use this method. Why we don't use something else is because we try to align ourselves to this international standard. Okay. First one we are going to see is the concept of the assay number. This parameter here is direct link to the free fatty acid content. So we are going to link these two concepts together, the acid number and the free fatty acid. We are going to link them together to talk about that part. The second one from this table here is the water content. Basically how much moisture inside of the with cooking oil, even in the biodiesel, whether they affect the quality of these products or not. So we are going to follow this method. For example, use the colorimetric method to analyze the water content. The first assay number basically is the free fatty acid content or concentration. Normally we call it content. More conventional way, we use the titration method. Okay. This is how we are going to use this table here. This table is adopted. This one is from another protocol. If you are interested, you can approach to me. We can talk about more details, the technical details for exploring more information. Okay, now we talk about the assay number. Is we know is related to the free fatty acid. Actually, the acid number is the concept is how much is the acid. So all the acidic components, okay, whatever the acidic components, we want to know how much. Basically, a sum up parameter. And commonly say fatty acid only have the one carboxylic group. Basically, one molecule have the one acid group. That's why we commonly use it, can just empirically just sum them up. One molecule of the COOH group. So that is somehow we characterize this assay number. And this number is very important because the higher assay number will affect the stability of the biofuel. Basically, say if we have a biodiesel inside or the feedstock, inside you have a high assay number, it means they cannot store for too long time. Meanwhile, we also know the corrosive effect. Basically, acid have some corrosive effect. We know that part. The higher of the acid contents, they will increase or they will get severe corrosive effect. This also means now logically we understand that we want acid number to be smaller. So the lower this value is, the quality of the products or this material will be higher. Okay, so we know the meaning of this assay number. We also know which part of basically high or low, basically we want this assay number to be lower. How do we detect it? How do we measure it? Okay, so we are going to titrate it. Titration method is just now from the previous page. I believe you still remember. We are going to titrate the sample with the potassium hydroxide. Before we do titration, we also know most of the fatty acids, they are not inorganic, right? And the titration, I believe you learned in PIPC subject. We normally use the acid and alkaline. They do the titration based neutralization reaction. They are in a water solution. But for this case wise, we can imagine the fatty acid ester will not dissolve in water. That's why we need to change the solvent system. And this system can be the ethanol and diethyl ether mixture, which not commonly or conventionally we make it 1:1. Basically, it's one portion of ethanol plus one portion of the diethyl ether. Diethyl ether and ethanol, the portion, we commonly use the volume rather than 1 gram to 1 gram or versus 1 milliliter to 1 milliliter. The latter one, okay, will be more practically to use. So we are going to dissolve these fatty acid esters or the feedstocks or samples with cooking oils inside this solvent system, then later time titrate it with this KOH or potassium hydroxide. Regarding to the titration, there could be two approaches we can go. Okay, one is go to the manual way. So we have the mixture, we also have the potassium hydroxide solution, then we do the titration. I will use the burette. Another way, possibly we can use some equipment. Nowadays, a lot of the very nice developed equipment can help us to do this type of job. We will see slightly later for the equipment type. We are not going to discuss more on the manual part because I believe you are well trained on the manual titration. Okay, we know the method. Now we need to know how to determine it, basically how to do it or how to calculate it, right? So now the reagent, we know we are going to use the potassium hydroxide. The solution-wise, we are going to use 0.1 mole per liter. Also, sometimes we can call it, try to use my stylish pen and write on me here. So sometimes we can, oh, I need to change this one. To use the pen here, yeah. So sometimes we also write it 0.1 m. Okay, that is the same meaning. Okay, in IPA means not in water. More or less, some of you maybe know this IPA means isopropanol or isopropane alcohol. Okay, I'm not going to draw structure here. It's not organic chemistry lecture. The with cooking oil mass, we also need to know how much sample we are going to weigh. Okay, if we know it's in a gram weight, no problem. We just use our balance to weigh it. Or just in case, okay, just in case you are offered the sample, which is the solution itself, give you the concentration, then you know the concentration times the volume. You can also calculate how much is the mass, right? So it could be deduced if some of the conditions given to you. Then the sample will be dissolved inside the solvent, which use the 1:1 volume over volume ratio of the ethanol and this ether. Now we have the potassium hydroxide solution. We also have the squeeze cook oil solution. Then we can just do the analysis. This is the typical equipment can do the titration job for us. For your reference, they will roughly look like this, okay? And the machine will read what? Read, let's say before the titration, there is the potassium hydroxide volume reading. When we say consume, basically there's available reading. There is some either screen or some reading panel, you will see it. And after the machine done the titration, they also have another reading. Basically, the reading is after titrate the sample, the leftover of the KOH there is the ending point. Basically, the starting point or ending point, or blank or the ending point, whichever you want to understand it is okay. So the difference of these two volumes, okay, the difference I would see some of the machine or some of the conventional parts, which value is higher, which value is lower is not that fixed. That's why I use this bar on both sides of this volume endpoint minus end of the volume of the blank, because we want to know the absolute difference. We want a positive number, basically say. This means how much the volume, sorry for this here. Okay, I will change it slightly later for the lecture notes. The consumed, basically how much the potassium hydroxide volume used. If we know this volume difference, how much they used, we also know the concentration is 0.1, then we will know how much this chemical potassium hydroxide used. And since the acid and the alkaline, they are the equal amount of the molecule. Basically, it's one molecule of the acid, they will consume one molecule of the alkaline to neutralize, right? That's called titration for this case. They will build a correlation in between. We are going to use this correlation to calculate or to determine the acid number. So here, if we know the volume of the potassium hydroxide we use, can just be standard, just use the liter first. Then the concentration is 0.1 mole. Okay, so this is how much molar of this KOH used. The mass of this KOH is how much, because it will times of this molecular weight of the potassium hydroxide, which is 56.1. You like the 0.1 be there, it's okay. So now you will just consider this. Okay, I change to my laser pointer again. So this 1, 2, 3, we just consider these three parts. It means how much gram of the potassium hydroxide used. If we are going to convert the unit a little bit more, basically plus this part, there will be how much of the potassium hydroxide in milligram format, or how much milligram KOH used. This is 1 gram of the waste cooking oil or sample oil. That is the definition of this acid number. So this acid number is one acid number, or the acid number is 1 gram of this oil sample equal to, or need to consume how much the milligram of the potassium hydroxide. So if we are going to just simplify a little bit here and there for this equation here. See, this is the liter, right? This is 1,000. 1 liter times 1,000, I can be, okay, I will change to my pen again, so we'll see clearer how this part. You will see, we cancel this gram, cancel this gram. This mole is mole per liter, we know that, right? So the mole will be go away, mole will be go away. This liter and this liter will be go away. Okay, they are the same, okay? They all go away already. So now this is the milligram left over, right? So it's basically is some milligram, that is the unit. If we are all good with this part, then we can see the volume in milligram. In milligram, this is 1 gram, it's 1,000, okay? So that is, if we are going to change, this liter to, let's make it clear, okay? So this volume of the milligram, the KOH, times this one will be divided by, okay, I stop here first. Thank you. Okay, now we can start to calculate or determine or test our assay number. Since the assay number, the molecular amount, molecule amount equal to the potassium OH, potassium hydroxide, we can use the volume of the KOH times 2 its concentration, which is the 0.1 mole. I can just use my laser pointer again, this one. Then times to the potassium hydroxide molecular weight, then convert it into the milligram. So I think I can use the pen again, so we can just double check the unit. The big M here is mole per liter. So now milliliter and milliliter, they will be cancelled away. This liter here and this liter here will be cancelled away. Molar go away, gram go away. So the net unit here will be milligram. So this will be the milligram come from. Okay, so the 1000 value and 1000 value go away. The net calculated or need to be calculated is 0.1 times 56.1. So the final assay number calculated will be the volume of the KOH we used in the milliliter. That because here we use the milliliter, right? Use the milliliter, but the unit for this assay number is milligram. Okay, so the value of this part then you times off is 5.61. If we are going to clean it a little bit more, just a little bit more, so the volume difference, which is endpoint minus the blank here in terms of the milliliter, just times of 5.61 and divide by its mass. For example, if it is just 1 gram of oil sample, we do not need to convert it by, or we can say we divide by 1, still the same thing. That is the assay number of this oil sample. I pause here for a few seconds. So now, if we are good with calculation of this assay number, now we can go to the free fatty acid. And this green line here is adopted from the previous slides for our reference, okay? And we know the mole of the FFA equals to mole of the KOH. Then we are going to use this one to further calculate it or further express it. So we know the mass equals to how much mole times its molecular weight, right? So how much is this mole is the KOH? So we are going to use the volume of the potassium hydroxide times its concentration, then times the molecular weight of the free fatty acid, which all are good, but sometimes we are okay, or we have our assay number already. Possibly we want to use our assay number to calculate the free fatty acid, which make our life much easier. How? Okay, let's try it just for the next line or next few lines. You will see it. Basically, instead of using the volume of the potassium hydroxide times its concentration, we can use this part. Okay, basically the volume of this part, they can be equal to AN divided by 5.61 here, right? So because the, okay, just leave this 1000 here. I will explain it in the next line. So the AN divided by 5.61, then times to this concentration times its molecular weight. As for the free fatty acid, it's not a pure compound, as we all know, but practically or conventionally, we can use one of them to represent them, called oleic acid. The molecular weight for this one is 282. So we just rewrite it, this line a little bit more so we can see slightly clearer about it. Okay, so the fatty acid concentration, the percentage, basically is assay number. We know the assay number is in terms of the milligram of the potassium hydroxide, right? So we want to convert it into the gram. That's why this 1000 here. Okay, so don't be too afraid about this 1000 to be here. Anyway, we can just leave it here, let it be. So for these two parts, we convert from the milligram to gram. Then we are going to divide by 56.1, which is the KOH molecular weight. So we know the how much more, okay, how much more of this fatty acid. Then time is molecular weight, which is 282 times 100%, which can be the percentage of this free fatty acid contents. So for this part, if we continue to simplify all these units, for example, gram and gram go away, milligram goes away. You know this 100, right? This 100 is 1000. If we just cancel 20 here and 20 here, there will be 10. So if I just further, just one more step to express it, this 10 times 56.1 will be 561. Agreed? Yeah. So you will see this one, actually, this is just 1 over 2. So it's also equal to 0.5, which is acid number times 0.5 will be the percentage of the free fatty acid, which compared to this line here, looks simpler, right? So we can use this one for our next some examples calculation for this part. Yeah, this is the sweetest part for this calculation. If we want to calculate the mass instead of the percentage, we know 1 gram is acid number times half. Then we just multiply the mass of the oil sample. For example, I have 3 gram the oil sample. Then you know 3 gram times how many percentage, you know how much gram will be there. That is easy to calculate it. Just follow this formula here. Okay, I will briefly or very quickly go through two examples to give you a concept of how we are going to calculate this part. For example, we go from the TP cafes, kitchens, or whatever kitchens, canteens, we collect some of the waste cooker oil, and we do ask the machine, or we do ourselves. Maybe ask one internship to do it, then we will have just take 1 milliliter of this oil, and then we weigh it. Yeah, it's 0.8 gram. We now have this. We have this data, right? We use the 0.1 mole of the potassium hydroxide titrated. Then we know the result is 0.0011 liter used to titrate until it reached to the neutralized point. Now we see how are we going to calculate its acid number and free fatty acid content. Is it the percentage one or the absolute mass? Okay, how we are going to do it? We're going to move this table just slightly on the top corner so we can use it. Still remember how we calculate the acid number, right? Acid number equals to the volume of the potassium hydroxide in terms of liter if we want. Time is concentration, time is molecular weight, and convert it. Then we can just cancel all the units, sub in all the value, cancel all the units. Then we can have this 7.714 as a result. In case you are not too sure yet, then we can just cancel them together. Mole go away, gram go away, right? Liter go away. Then this 1000 times 0.1, all these numbers. Now you can use your calculator to calculate it. I trust you better to calculate it better because your calculation skill should be better than mine. This is the one way to calculate it. Somehow, was the point previous slides we learned how to calculate the acid number already, use some of the formulas if we still want to use it. Nothing wrong with it. So the volume difference here is 0.0011 is liter, right? At previous point we said we want to use the milliliter. So here we are going to time 1000 just to convert it into the milliliter. Then we still follow our 1.61, this is the factor, and divide by its mass itself. You will still get the same result. You can try it out. You can pause it here to try it out, okay? Okay, now we are good with this acid number. We can continue with this acid number for the free fatty acid, which is just divide by 2 or times 0.5. Up to you, which way you are comfortable to go. So for me, I just times 0.5. Then I know it's just half of it. Leave the percentage sign there is my habit. There's nothing wrong with it. If you are try to keep your decimal place rather than 3 to be 2, then you just round it up. Okay, so the free fatty acid content percentage-wise will be 3.89%. Of course, you say, that is 1 milliliter, 0.8 gram. I want absolute mass. If you want to present it other way, sure, you just times the 0.8 gram. That will be 3.11 gram of the free fatty acid in this 1 milliliter or this 0.8 gram of the oil sample. I think now you roughly know how to calculate use this way. In case it's a machine-wise, okay, just give you one more example here. I have the rough run, then I have 1, 2, 3 run. I have my initial and final ending point values. Then we'll know the difference of each of this value volume we used, right? Instead, I will just ignore this rough one because it's just rough test. Then I can average up my 3 runs. I have my average of the volume used or consumed. So from this data wise, we are going to calculate our acid number of free fatty acid. Instead of using all the previous logic, I can just directly use the ending point minus the blank, which is the difference of this volume here. I can directly use it. Okay, the mass here, the big M or the smaller m mass here, which is 1 gram of sample, we can just leave it as 1. Much easier to calculate. So that we use sub in all the values inside, the volume in 5.61 be there, then you can calculate the volume will be 7.76 as the acid number. If we know the acid number already, the free fatty acid percentage will be this times half, which is 3.88%. So no matter we use the machine or manual or repeat it 3 times or even more than 3 times, you know how to calculate this free fatty acid content and acid number. The second concept here is the water content. Water content, as the introduction part, we know it is not welcome, basically harmful. We treat it as a contaminant. Okay, it hydrolyzes the ester bonds. It will consume the sodium hydroxide. You will use this as the catalyst for the transesterification reaction. So what we want is this biodiesel, or we want whatever with the low water content. If this water content is high, they will make this sample have the lower oxidation stability. This means what? It's much easier to be oxidized. Something being oxidized is not a good sign for the biological parts or for the chemical parts, for our skin, our food or whatever. So it means being easy to be oxidized, not easy to store. and surely it's not good for our engine. You will use it as a fuel. Okay. For the Union, European Union, the area, the standard, they set the limit such as 500 milligram per kilogram. That is the high limit for that part. For your reference, okay, just for your reference. The detection method here is called colorimetric Karl-Fischer titration. Even there is the titration word here, as people seldom really use the titration method. We ourselves do the manual titration. You might see the fade out picture on top corner here. It's equipment can detect this water inside of our oil sample. In case any of you later time you will going to pursue more projects or some of the internship, for example, you need to know more detail about how to determine the water content. Here I provide a reference for you. Basically the European Union standard. This is the title. You can just search and Google to find the detailed technical information from it. Okay, I think now I will pause this topic here to wrap up as the lecture part 1 to prevent the lecture is too long to tire you up. I believe now you want to have a small break. Let's pause here, continue to the next lecture for the next parameter. I'll see you soon.